All right, welcome. Let's take a look at this problem. Looks like we're given an equilibrium system and we're asked to determine the partial pressure of a product when the system reaches equilibrium. And then we're given some numbers here. So whenever we're given some numbers, asked to do a calculation involving equilibrium, often an ice chart is a useful strategy. So I'm going to try and set up an ice chart to help organize this information that I am given. All right, so we know the initial partial pressure of N2O is 1.1 atmospheres. So that goes right there. And then the initial pressure of NO2 is 1.9 atmospheres. And that's it. It looks like only N2O and NO2 are placed into the container. So that means this starts out at 0. And it looks like I am not given any other value. So everything else now is an unknown. So I'm going to use X to represent my unknown. So what I know is that N2O and NO2 are going to react. So some of these are going to get used up and they react in a 1-to-1 ratio. And then they're going to make product. But notice how this is we follow a 3-to-1-to-1 ratio. So this number is going to be 3 times these numbers. And my reactants are getting used up. So that's a negative number. My products are being formed. That's a positive number. And then my initial plus my change is my equilibrium. So 1.1 minus X, 1.9 minus X, and then this is just 3X. And this just helps me organize information so I can plug it into a K expression and solve. So let's set up my K expression here. So it's going to be, products over reactants, coefficients become exponents. I leave out any solids or liquids. No solids and liquids here. So that's my K expression. And now I'm going to go plug in some numbers. So K is 6.6 times 10 to the negative 6. PNO is 3X, and I'm going to cube it. And on the bottom, it's 1.1 minus X, and then 1.9 minus X. So I could solve for this, in theory, right? I have one unknown, X, and then one equation. But this would get kind of complicated here, the math. So I want to look out for, is there a simplification I can make? And notice how this K value is pretty small. So K is at least 3 orders of magnitude smaller than these initial concentrations. So therefore, we can make our, K is small or X is small simplification, which is that 1.1 minus X is just 1.1. And 1.9 minus X is just 1.9. So I come over here, and I'm going to simplify this. So the bottom now, instead of 1.1 minus X, I'm just going to say, oh, that number is just 1.1. And this number is just 1.9. Whoops. And now this makes the math a lot easier. I'm just going to take this number and multiply it by these numbers and then, divide and things like that. All right, so we start doing some algebra here. Let's simplify this. So 3x cubed, don't forget that this is a cube. Often we square things. We maybe haven't cubed them before. So 3 cubed is, let me write this over here, is 27. So it's 27x cubed. And then over here is going to be 6.6 times 10 to the negative 6. And then we're going to multiply that by, 1.1 and 1.9. And then we're going to divide both sides by 27, and then to solve for X, we're going to take the cube root of this whole thing. So stop and do that in your calculator if you haven't already. So when I plug that in my calculator, I seem to be getting that X is equal to 0.00799. Looks like I need to round it to 2 sig figs though, so I'm going to round it to 0.80. And then units here, this is in atmospheres because this is a KP that we are dealing with. So that means all of these values here are in atmospheres. And then I got to make sure I answered the question. So the question didn't necessarily ask me to solve for X. It said, determine the partial pressure of the product NO. So if I look back at my ice chart, I actually defined NO, the partial pressure of NO, as being 3X. So to actually answer the question, I have to take my answer, and multiply it by 3. So I get 0.024 atmospheres as being my final answer here.